Structural geology. Fault, joint, fracture, faults, thrust. Fault. When rocks deform in a ductile manner, instead of fracturing, they may bend or fault, and the resulting structure are called faults. Faults may develop in any type of rock and may be of any shape and geometry, ranging from simple upward bends or downward curvature to completely overturned. The process of folding is very slow geological process. Parts of a fault: limbs, the, the side or flanks of a fault. An individual fault will have maximum two limbs, commonly the left and right limb. Hinge. The limbs intersect at the tightest tight, tightest part of the fault called the hinge, maximum curvature. An imaginary line that shows the location of maximum curvature on a fault is the hinge line. Fault axis. A line connecting all points on the hinge is called the fault axis. Axial plane. The imaginary plane passing through the axis of fault. Core. It is the center of fault. Classification of faults. Faults can be of variety of forms. Some may be quite simple and clearly developed, whereas others may be highly complex and complicated in their geometry and morphology. Basically, faults can be of two types according to their forms: anticline and syncline. Apart from them, faults can be classified according to their position of axial plane, interlimb angle, and orientation of hinge line and axial surface. Anticline. These are the faults where the strata are upwards. That is, these become convex upward. Oldest rocks are found at the core and youngest at the outermost flank. The highest part of the anticline is called the crest. Limbs dip away from one each other at the crest. An anti an anticlinorium is a series of anticlinal faults on a regional scale anticline. Syncline. The fault in which the strata are downwards and become the convex downward form. Younger rocks occupy the core and the older rocks forms the outer flanks of the fault. The limbs dip toward the common center. The lowest part of the syncline is called trough. A synclinorium is a series of synclinal faults on a regional scale syncline. Some structural geologists prefer the terms antiform and synform for upwards and downwards folding respectively, unless the stratigraphic order is completely established. Types of fault based on the position of axial plane. Depending upon the nature and direction of the stresses, the axial plane in a resulting fault may acquire any position in space. It may be vertical, inclined, or horizontal. Symmetric fault, asymmetric fault, overturn, recumbent, isoclinal, chevron faults are some type of faults. Symmetrical fault. If the two limbs of the fault dip away from the axis with the same angle, the fault is said to be symmetrical fault. The axial plane is vertical. Asymmetrical fault. The faults in which the deep amount of limbs differ with each other. The axial plane is inclined. Overturn fault. The faults with inclined axial planes in which both the limbs are dipping essentially in the same general direction. The amount of dip of the limbs may or may not be same. Isoclinal fault. If the compressional stresses that cause the folding are intense, the fault can close up and have limbs that are parallel to each other. The dips of both limbs are equal and so are the axial planes, which can be vertical or inclined. Recumbent fault. The fault in which the axial plane is horizontal. Chevron fault. A fault that has no curvature in its hinge and straight sided limbs that form a zigzag pattern is called chevron fault. Walls on the basis of interlimb angle: gentle, open, close, tight, isoclinal. Gentle 180 to 120 degrees. Open 120 to 70 degrees. Close 70 to 30 degrees. Tight 30 to 0 degrees. Isoclinal 0 degrees. Classification according to orientation of hinge line and axial surface. Orientation of hinge line. Vertical dipping horizontal, horizontal plunging particle. Recognition of faults in field. Local or small scale faults are directly observed in the field in cut slopes during road construction, excavations, or drilling for special purpose. But many times fault in the field will be inferred by looking at the attitude of the beds. Large scale faults are recognized in the field by plotting the attitude of the beds or foliation plane in the geological map and their cross section. The repetition of beds in the field and varying thickness of strata in one place, then order of the same geology also will indicate faults. Engineering consideration significance. Faults develops in the areas of work are important for a civil engineer in that this make the work more complicated. If not investigated and interpreted thoroughly, civil engineering projects standing on or driven through the folded rocks may be proved to be uneconomical and unsafe too. Presence of faults will influence the design stability and economy of large scale structures like road, tunnels, dams, bridges, etc. Medium scale local faults are usually of more concern than those of a regional character. Folding of any type will cause the change in attitude of the same strata. Same layers may be repeated along an alignment, or one or more layer can be encountered unexpectedly. If the unexpected bits are of undesirable nature, then it may affect the time schedule and cost of the project. Faulting is the response of rocks to the stress induced to them. These stresses are strong enough to break or shatter the rock, especially in the axial zones, which are the places of maximum concentration of these forces. These fractured or shattered zones are weak in strain and porous in nature. Such areas cannot be trusted as roofs and floors of a tunnel, so axial regions in the folded rocks will be truly studied and avoided if possible. If not, should be treated. Folded rocks are considerably strained, and when there is an effort by nature or by an engineer to disturb the adjustment, the rock may respond by release of some strain energy. This release of energy is evident in the tunnel excavations where huge blocks of rock start caving in a falling in great force called rock burst. Discontinuity in geotechnical engineering, in geotechnical literature often denoted by joint, is a plane or surface that marks a change in physical or chemical characteristics in a soil or rock mass. Or discontinuity can be, for example, a bedding, cystosity, foliation, joint, cleavage, fracture, fissure, crack, or fall plane. Discontinuities formed by deformation like joint, fault, and fracture are explained in brief. Joints are the divisional planes or fractures along which there has been no relative dislocation, which result from strains of tectonic origin and often fall into defined states whose members are oriented essentially parallel to each other. Joints are important in many kinds of geological and engineering geological studies. In some cases, these are more prominent prominent than beddings and have much more role in the stability than the beds. Joints are the planes and ends have an attitude. Joints may be open or closed. Open joints are those in which the blocks have been separated or open up for a small distance in a direction at right angles to the fracture surface. This may be gradually enlarged by weathering process. In closed joints, there is no such separation. Even then, joints may be capable of allowing fluids, gases, and water to pass through the rock. The open joints are commonly filled with minerals. The infilling tends to reduce shearing resistance along the joint surface. Joints may form as a result of either diastrophism, tension, or contraction. Most joints are tight fracture initially, but because of weathering, the joints may be enlarged into open fissures. Classification of joints. Joint can be classified either genetically or geometrically. Genetic classification. Tension joints. Tension joints are commonly tension joints are tension joints are those tension joints tension joints are those which have developed due to the tensile forces acting on the rocks. The most common location of such joints is in the outer margin of a folded sequence. Shear joints. Shear joints are commonly observed in the vicinity of fault planes and shear zones where the relationship with the shearing force is clearly established. Compression joints. Compression joints are the joints due to compressive strain and the rocks may be compressed due to crossing and numerous joints may result. In folded sequence, the compression joints are formed in the core regions. Geometric classification. In a geometrical classification, two joints may be classified on the basis of their attitude relative to that bedding or other similar structure in the rock that they cut. Strike joints, dip joints, oblique joint, bedding joint. Strike joint. Strike joint. The joint that strikes parallel to the strike of the bedding or foliation of a rock. Dip joint. The joint which strikes parallel to direction in which the bedding or foliation dips. Oblique joint. The joint which striking in a direction that lies between the strike and direction of dip of the associated rock. It is also called as diagonal joint. Bedding joint. Joint parallel to the bedding of the associated sedimentary rocks is called a bedding joint. Causes of jointing. Contraction during formation. Sedimentary rocks which are rich in moisture in the initial stages undergo some contraction or on drying up which results irregular jointing. Similarly, igneous rocks when cooling necessarily undergo considerably contraction during the cooling process, giving rise to tensile forces strong enough to break the mass into jointed blocks. Expansion and contraction. Repeated heating and cooling during daytime and nighttime in the dry hot climate will eventually develop crack and fissures in the rock. Removal of overburden due to weathering or other process will cause the expansion of the underlying rocks due to unloading. The previously loaded rocks gets relaxed with the release of the force, and joints may appear parallel to the surface of erosion in such exposed rocks. Crustal disturbances. Many joint types, especially associated with the faulted rocks, are clearly related to the process of crustal disturbances responsible for mountain building processes. Certain seismic waves have also been suggested by some as possible cause for the development of joint in many rocks. Systematic sets will be distinguished from non-systematic sets when regarding discontinuities in the field. Barton 1978 suggests that the number of sets of discontinuities at any particular location could be described in the following manner. Massive occasional random joints, one discontinuity set, one discontinuity set plus random, two sets, two discontinuity sets plus random, three discontinuity sets, discontinuity sets plus random, four or more discontinuity states, cross rock or like. Engineering considerations. The selection of sites for dams and reservoirs and alignment of tunnels and highway to require very true investigation of joints for arriving at safe and economic design. Joints are always considered as a source of weakness of the rock and as pathways for the leakage of water through the rock. Both these properties of joints destroy the inherent soundness of the rock to a great extent. If a rock forming the foundation of a dam or reservoir happens to be heavily jointed and region is one of the low water table, the risks of leakage of water from under the dam or from reservoir may be of substantial magnitude, demanding very heavy cost for treatment of rocks. If the roof and side rocks in the case of tunnel are much fracture, slippage of rock along these fractures and leakage of water may cause many troubles. A large joint dipping into the highway cut is the site of potential landslide. Jointed rocks easily gets lubricated in the presence of water and start sliding or falling from the original places of occurrence. Occurrence. Many landslide and slow failure are Many landslide and slow failure are directly related to the jointed nature of the rocks. Treatment of joints. Treatment of negative qualities of rock due to joints vary in different projects. Detailed investigation to establish full characteristics of the joint in terms of their type, frequency, intensity, pattern of distribution, and extent to which they influence has to be carried out. Treatment of joints may involve grouting, injection of construction material similar to mortar into the voids to seal the joints with a suitable grout for increasing the strength of the rock and reducing the permeability. Bolting of the rock blocks formed due to the jointing is another method of treatment. In slopes where intersecting planes may be cause of failure, shortcut can be used to treat the joints. Fault. A fault can be defined as any brittle deformation induced fracture where there has been movement of the blocks on either side of the plane. A fault line is the surface trace of a fault, the line of intersection between the fault plane and the earth surface. Since faults do not usually consist of a single clean fracture, geologists use the term fault zone. The two sides of a non-vertical fault are known as the hanging wall and foot wall. By definition, the hanging wall occurs above the fault plane and the foot wall occurs below the fault. Generally, we cannot determine which side of fault has moved. It could be either or both. All we can tell is the relative motion between them. In measuring the horizontal or particle separation, the true of the fault is the particle component of the deep separation and the heave of the fault is the horizontal component. H is equal to heave of the fault, T is equal to throw of the fault. Types of fault. Faults are classified generally based on their geometry and origin. Genesis. Genesis. Different types of faults may be deep sleep faults, normal fault, reverse fault, thrust fault, strike slip fault, particle fault, particle fault or oblique fault. Geometric classification. Deep sleep fault. The type of fault in which the movement is mainly parallel to the deep of fault surface may produce long, low cliffs called fault scarps. Parts of a deep sleep fault include a hanging wall, rock surface above the fault, and a footwall, rock surface below the fault. Normal, reverse, and thrust faults are examples of deep sleep fault. Particle fault. The fault in which the fault plane is particle and the movement is also particle. Oblique fault. A fault which has a component of deep sleep and a component of strike slip is termed an oblique slip fault. Nearly all faults will have some component of both deep sleep and strike slip. So defining a fault as oblique requires both deep and strike components to be measurable and significant. Strike slip fault. Dominant displacement is horizontal and parallel to the strike of the fault. The block of rocks move laterally with respect to each other. Genetic classification. Normal fault. Hanging wall blocks move down relative to the footwall block. Accommodate lengthening or extension of the crust. When the rocks move apart, the side with the less stable tectonic plate drops below the side with the more stable plate. Most are small with displacement of a meter or so. Larger scale normal faults are associated with structures called fault block mountains. Reverse fault. The fault in which the hanging wall block moves up relative to the footwall block. Accommodate shortening of the crust, strong compressional forces. Thrust fault. When the reverse fault plane has a dip of less than 45 degrees, the reverse fault is termed a thrust fault. By definition, thrust is a low angle that is less than 45-degree reverse fault. Thrust fault bring the older rock sequence over the younger one. Effect of faulting. Faulting is essentially a process of rupturing and displacement along a plane of rupture. It is only from a geological map that a existence of faults and their effect on a rock may be established with some certainty. The effect of fault may involve change in elevation of ground, omission of strata where they are normally expected, repetition of some strata in a given direction against the normal order of superposition, displacement and shifts in continuity of some rocks in certain regions. Field identification of faults. Recognition of faults on the ground very often demands a through and systematic geological and very often geophysical study of the area, often to a often to a considerably depth. Very common characteristics field evidence of a presence of a fault can be presence of silicon site. A silicon site is a smoothly polished surface normally straightened in the direction of movement caused by frictional movement between rocks along the two sides of a fault. An exposed or covered surface may be suspected of being a fault surface. It is polished and carries grooves and striations. Similarly, presence of braceted zones and shear fold gouges, gouges indicate a possibility of a fault. Normal sequence of rock strata are disturbed in an area of faulting. A group of beds may abruptly terminate along a surface in a given region. Some beds may repeat and found in more than once in certain section, and some may be omitted where it was normally expected. This disruption of beds or displacement of beds due to faulting may be observed. In some regions, a number of springs may occur along a slope in the almost the same line. Sometimes stream may show an interruption or offset or break in their profile due to faults. In many cases, the geophysical method employed for various applications may indicate the presence of fault. Engineering significance of fault. Fault are the region where dislocation of ground has occurred in the past due to deformation and where such dislocation cannot be entirely ruled out in the future. The faulted rocks will form weak foundation despite the fact that the rock originally might have been strong. The share of fault zone will be easy pathway for water and cause leakage if left untreated in dams and reservoirs. Fault plains with easy pathway for groundwater creates problem if encountered along a highway or tunnel alignment. Highway or tunnel alignment. The fault zone, once lubricated by water, may slip further and prove critical for foundation and abutments. Fault gauge and breccia may create additional problems, and and they have they may have to be cleared to the sound bedrock for construction in the site. Major fault zones are prone to landslide due to flagial earth metal and may cause problem during construction of various projects. The engineer has to consider fault in these angles. What have been the effect of faulting in the rock in the proposed site? How far the rock of the site will be suitable from strength point of view? Can structure be still built on them with or without some treatment of the fault whose effect has been negligible in the present? Is there probability of the faulting again during the lifespan of the project? What factor of safety is essential to be adopted in the design and construction of the proposed structure if the faulted site has no alternative? The presence of faults, their type and extent and their effect on the project area can be ascertained by engineering geological map and geophysical data. The number, size, and inclination of shear zone must should given consideration. Ideally, projects are to be located far from an active fault and never on the active faults. If the site could not be relocated, the treatment of the shear zone, extensive excavation of sheared metal and backfilling with cement grouting may be a solution to a problem. Many major faults may be associated with earthquakes, so the project sites will also be considered with respect to the seismic zoning of the country. Even if the evidence of the study show that the shear zone will have no movement during the lifespan of the project, some factor of safety should be considered while constructing in a shear zone. So this was for today.